Ate some food. Now we're back at it. Now I need to refresh my memory as to where I actually was. What was going on? Okay, we had just sorted the equations before constructing the system. I need to cut my nails. Get some more water and then cut my nails. Okay, and the reason why we wanted to sort the equations was because we need to make sure that when we're constructing the A hash map, which is a map that refers vertices or v nodes with their derivative v nodes. And the problem is that we need to make sure that those node indices are correct. And currently the function that we use to make those the A map doesn't actually construct it from the graph itself, which we could do. And alternatively, what I was thinking is that maybe if they're sorted... Oh, no, yeah. So what I was thinking is that I think that this would not work, but what I was imagining is maybe if when if I change the constructor or the build bipartite graph function, if I insert all of the equation nodes first and then all of the sorted vertex nodes, then presumably I could just offset it and I could just I don't think that would be bad, but some part of me thinks that would be bad. But I don't know why. Okay, so let's build our electric boogaloo function. And so the first thing we do is we want this actually to be a stable ungraph. Creates a new stable with estimated capacity. Huh. usize? Is there a type max function? fine. I mean, I'm not going to get hung up on this. No, but does that allocate the whole thing? I don't think I want to do that. Okay. Okay, cool. So oh shit. I don't know why that's not a thing. I'm sure that Rust, they really care about correctness, so so then we for eq in, oh yeah, we want to copy over this thing too. Do we want to maintain an index map too? So instead of just a hash set, what if we did what would it be? It would be no, this is fine. Wait, what? Why did I think this was broken again? For one, unary op is just not handled. I forgot. There was something here that was like super sus. Oh no, I think it's in a create the association. I never know how to organize. Okay, so And then when you collect a vec, it doesn't actually... So these are going to be our V nodes, and then these are our E nodes. Oh, that's so nice, actually. Wait, does that work? Is that what you do? Oh, that's so nice. Cool. You just leave that at the bottom and then you do what you need to do. Okay, so we want to do... We want to do... G... I think I can actually just do this. Okay, cool. Okay, and then... No, so we should assume. Right, so we can do. Oh, this is the. Kind of love Zen mode, not gonna lie. I wish I could. Oh, nice. Yep.
You know what I'm talking about?
What?
You know what I'm
Okay. Shit. What was I doing? Oh yeah, I'm testing the new. Nice. Okay. Okay, what is it? You do. Okay, let me actually. How do I close this thing? Okay. You do config test config. Okay, so let me just write it. Config tests, test, mod tests. What does super mean? Okay. So what did we just do? We now build partite graph has an what is the number of edges there? Doesn't matter. But now what we need to do is we need to build the A association. And so I guess label is called to string. I wanna feel something, but I don't feel nothing. So do I want to build A just from the graph? Because it seems like that's what I'm trying to do, but in reality, But in the paper, I mean, the way that the equations are structured, I could get these. In a lot of ways, it really makes sense for me to have my own bipartite graph type. Because it's just so annoying to keep track of this. Okay, but we have a set. Okay, so if we just said that these were... Alright, let me sit with it for a little bit. How does it get used? It gets used by being indexed, but I'm glad that we're here. We at least got to this. We built the correct bipartite graph. I would like to print that out, actually. No, it's wrong. So we're not constructing the graph correctly because this code is wrong. Oh, that's definitely wrong. No. Extract variables is wrong. Is that true? X dot is only in F1. That's W. W seems to, okay. This is equation 3. I don't know how to resolve that. Like, but interestingly, in this one, X is not incident. Oh, X is incident. Never mind. Yeah, so we want to stop recursing if you hit the dir. Let's add an assert here that okay, but then if we do this, okay, that might be, oh, it kind of looks like the same. Hold on. Node count, g.edge count. I don't want to count that. Okay. Is that right? Yeah. Y occurs in 2. I think that's right. You stop recursing if you hit a dir or a var. Alright, I'll sit there and count these things out. 1, 2. Oh, this is such a pain in the ass. 1, 2, 3, 4, 5, 6. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nice. Okay. Alright, cool. So I'm starting to understand my code too, so I'm glad that I was able to make that change because it does seem like this is correct. I'm going to change binary op to bin op. Go even further. Uop and bop. Now this is fine. Okay, so now we need to construct A. So we should be able to Oh, that's so useful. That is so useful, dude. Oh. But what we want to do is, for every vertex, yeah, we could just make it simply run an n squared. Yeah, naively we'll make it run an n squared because I don't really care about performance at this point. But so for every vertex, we look at every other vertex, and we say, we match on the vertex weight. So does indexing give me the weight? Let's see. Wait, why is it a string? No, bruh. No. Yeah, so in the dir case, we're assuming order 1, so the dir case we don't do anything. But if you find... Yeah, okay, so fine. So match var... What? What? I'm certain that in here, match expert var. String. Expected fat arrow. I have a pointer to boxed enum, and I want to match on the enum how to do. Yeah, didn't I do that? Do I need a double dereference? Oh, there we go. Oh, wait. No, now we want to... Oh, we want to say x to var. No, we want their node indices, though. Oh, it was right all along. It was smarter than me. Okay, so this is handwritten, though. I mean, clearly not good code. But we don't need the E nodes, we just need the V nodes. And we don't need the edge indices either. Okay. Let A equal but wait, build a built it from the graph, which may turn out to be totally wrong. I'm at least pleased that I was able to write that myself, despite it being awful, awful, awful code. Oh, I should probably zoom in a little bit for the stream. I mean, no one's watching anyways. No, but it's worth it. Okay. Dude, Match is sweet. I love Match. Do 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 do. Almost bonked myself. Now with this map, it should be easy to Oh, wait. Nice. Do 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 do. It's a long road to get to what I actually want to do, which is simulate circuits. Okay. Let's go back to the paper. So now I want to implement this thing. Alright, so I want to print out those things. Constantinos. I want to look this guy up. This dude's a badass, man. Oh, nice. Is that if... That's cool.
Differential and algebraic equations are composed of, I'm going to show you and that can also solve the index 1 DAE form. It can also solve an index 2 in the Hessenberg form. So there's a couple options for solvers that are out there. But let's say we just wanted to solve it in index 3 form. So I'm going to show you, first of all, the index 3 form, and then let's go back and do the index 0 form, the ODE form as well. Okay, so I'm just going to type this out, or have Notepad type this out for me. Okay, so here I have the model. You can see the equation. This is our x squared plus y squared equals s squared, and then we have our other equations there. that relate the velocity in the w and in the v, the x and y directions. You can see some of those.
Wait, is this
we
the
have those on
pendulum?
y. Right there.
No.
As well. Okay, so there are the 5 differential equations that relate these different variables to each other, and then we also have some supporting variables as well. All right, so let's go and solve this one. I just want to show this one to you. I'll do the index 3 one first of all. And the way that it does this is it uses orthogonal collocation on finite elements and solves it with large-scale and sparse solvers. So you don't need to be able to transform it into an ODE form or an index 1 DAE form. It solves it directly as an index 3 differential and algebraic equation problem. Now you can see here there's no numerical drift. Position, x and y, those are stable from cycle to cycle. And so overall the solution looks good. Let's go and do our next one now, which is going to be the index 0 DAE. All right, so I'm going to have, let's go ahead and close this one. Close this one. I'm using Notepad++ to do some ghost typing for me. Animate this a little bit. Okay, kind of fast there. A little bit too fast for explaining the code. But essentially, I'm just creating the Gecko model. And you can solve this problem with almost any ODE integrator. You'll see that all of these now are in this differential equation format, where all of them are on this left-hand side of the equation. And you can set up an ODE solver pretty easily to solve this.
Oh, shit. Dude, this is sweet.
Okay, and let's go ahead and simulate it though, and just see the results of this. So I'm going to show this with Ideally. I'm going to edit and run it. And you'll see some examples here of that numerical drift that I was talking about. So here on the top plot, you can see the y value, how it's trending down over time. You can also see the lambda value at the very bottom, how that one is also trending down over time. So it's just this numerical drift because we've had to differentiate it 3 times to get it back to the ordinary differential equation form. So one of the other advantages of solving this with the simultaneous method, and be able to solve these higher index forms, is that you don't necessarily need to rearrange the equations to get them back into a particular form. You can solve it with the ones that are most natural to write, like straight out of a textbook, for example. You don't need to make a lot of rearrangement. You'll notice this especially in situations where you have something like a distillation column. Okay, you'll see that those are going to traditionally be something like at least an index 1 or an index 2 DAE. I've seen a lot of people that have to rearrange, okay, the equations to get them into the index 1 form. It takes a lot of rearrangement to be able to simulate this distillation column to get into that particular form. But if you can just solve it directly as an index 2 or index 3 problem, then you can focus on the equations and don't have to focus so much on rearranging the equations to fit a particular solver that can only handle certain forms. So the other nice thing about this too is I wrote it out at the beginning, this way for my differential equations, and then 0 equals g of x. The other nice thing is that you don't even have to have this in the semi-explicit form like that. You can have everything on one side of the equation or the other. So it's actually more like this that I've just put in this box, that you don't even have to have the differential terms separated from the other. You can solve them all simultaneously in this combined method. Okay, so let me just show you the source code for this. This is, if you want to try this yourself or other problems, it's here under this pendulum motion in the documentation for high index DAE solutions. If you just search for it, also put this link here in the video description. And it has just an explanation of the simple problem with the pendulum, the index 0 to index 3 forms for the equations, and then the source code here for each of those. So you can see index 0, index 1, index 2 code, and then finally the index 3 DAE code. If you want a little bit more information, this is also an article on initialization. So just with the index 0, if you get it back to the ODE form, then you might have some numerical issues. Also, there are many solvers that can solve an index 1 form. Many of the solvers in Python or MATLAB can solve that. ODE 15s is a good example of a DAE solver in MATLAB. Okay, so, and that can also solve the index 1 DAE form. It can also solve an index 2 in the Hessenberg form. So there's a couple options for solvers that are out there. But let's say we just want to solve it in index 3 form. So I'm going to show you, first of all, the index 3 form. And then let's go back and do the index 0 form, the ODE form as well. Okay, so I'm just going to type this out, or have Notepad type this out for me. Okay, so here I have the model. You can see the equation. This is our x squared plus y squared equals s squared. And then we have our other equations there that relate the velocity in the w and okay, in the v, the x and y directions, you can see some of those. Okay, we do have the Lagrange multiplier there as well. Okay, so there are the 5 differential equations that relate these different variables to each other, and then we also have some supporting variables as well. All right, so let's go and solve this one. I just want to show this one to you. I'll do the index 3 one first of all. And the way that it does this is it uses orthogonal collocation on finite elements and solves it. We're going to talk about orthogonal collocation on finite elements, in particular how to use this to solve differential equations. So for example, if I have dx dt equals f of x, that's perhaps a nonlinear differential equation. And if you remember, just first of all, discretization method that you may be familiar with is Euler's method. And in Euler's method, we have 2 points, our initial condition that we know, and then our final condition, which is x1, and we just do a finite difference approximation for our derivative. So dx dt equals approximately...
What is that, applied physics monitor?
There. X1 minus x naught divided by the delta time. Okay, there's the change in time right there. Okay, and from this we can solve the differential equation by just putting our right-hand side of the equation back there, and then have x1 equals delta t times f of x plus x naught. So that's how we determine x1. So this is probably the most simple discretization method called Euler's, and we can also do this would be one of the simplest there. Okay, that's just with 2 nodes. Now another way to do this is through a orthogonal collocation on finite elements, and what we're doing is we have higher order or more accurate methods, and we have more points. So let's just go up to 3, where we have x naught, x1, and x2, and then we use a polynomial to fit this. So I'm going to just have a polynomial, which is x of t equals a plus, and then you have to have the same number of order of polynomial as you do points. Okay, so there's my x of t, and then if I have these 3 points, I'm going to essentially use this polynomial to come up with the derivatives. So if I have derivatives at x1, I can just take my dx1 dt is going to be equal to, and I take the derivative of that, which is going to be b plus 2ct. Okay, and that would become my derivative approximation that I would use right here, and solve the equation right here, dx1 dt equals f of x1, and then I have another one right here that I need to solve, which is dx2 dt equals f of x2. Okay, so I have essentially 4 variables and 4 unknowns. I have dx1 dt, I have x1, I have dx2 dt, and I have x2. Okay, so I have this equation, that's equation number 1. Here's equation number 2, and then I had equation number 3, and then I would have equation, number 4 as well. But we're going to rearrange this a little bit so that we can not have these higher order polynomials so we're going to go through the derivation of how to implement this more efficiently. But essentially what we're doing is, instead of the linear approximation that Euler's method gives us, we're going to do some higher order methods to be able to approximate our solution. They're going to be more accurate. Okay, so let's just go ahead and start. I'm going to start with a 4th order. Okay, let's just say I had x of t equals a plus bt plus bt plus c times t squared plus d times t to the 3rd, and the points I have are x0, x1, x2, and x3. So there are my points right there that I'm going to try to obtain a solution to. Okay, so the very first thing that I'll need to do is go ahead and just, like I did with these 4 variables, 4 equations right here, I'm going to go ahead and put this into a matrix form. And what I'm going to do is go ahead and just do x1 dot, that's the derivative of x, x2 dot, x3 dot, okay, equals an M matrix. And you'll see where this comes in just a little bit. I'll have x1, x2, and x3, and then I'll subtract the initial condition. Okay, so I'm going to put it in this form right here, and then I'm going to take this polynomial right here and take the derivative, okay, for each one. And so I'll have x1 dot equals b plus 2ct plus 3dt squared. Okay, and that's going to be at time 1. And then I have the next one, which is b plus 2ct2 plus 3dt2 squared, and then the final one. Okay, and just finishing that off. Okay, and then I'm going to substitute these right in there. And I'm also going to substitute these right in here because I know that x1, okay, it's no longer a function. I'm going to evaluate that at a particular point. Okay, so x of t1, okay, which is going to be x1, is going to be equal to, and then that's just going to be a plus b t1 plus c t1 squared plus d t1 cubed. Okay, I'm going to do that for all of them. And then we'll substitute those in, and then we come up with something that can factor out. And I don't want to skip a step here, so let me just go kind of painfully slow with a lot of detail here. Let's just go ahead and write this all out. Okay, I'm going to do b, okay, the very first one, plus 3d t1 squared, b plus 2ct2 plus 3d t2 squared plus b plus 2ct3 plus 3dt3 squared. Okay, and that's going to be on the left-hand side. And then I'm going to have this M matrix right there. And then I want to have my other points that are going to be in there. This one is going to be, the M matrix, which is, and then multiplied by, okay, so let's just do this. I'm going to write this out. It's going to be A plus BT1 plus CT1 squared plus DT cubed. Okay, A plus BT2 plus CT. Okay, so this is kind of the point where a lot of students get confused. We're going to factor out a B, C, and D. Okay, so plus B2 plus 3 T and 3 side T1. I don't need T. Is going to be equal to that one. Okay, so just like I have two matrices, if I had a matrix A times X plus B times X, I'll do an equal sign there, then I would know that A and B matrices are the same. Okay, so I have just these two left-hand sides that I'm going to equate to each other, and then from that I can get the M matrix. Okay, so now I have M. Okay, I didn't put these. I have T. So now I just derived my M matrix, and that M matrix inverse. So now I just derived my M matrix, and that M matrix goes right in here to relate our derivative equation because, but if we have time, okay, and that goes from 0. If we have different, but if we have if we have a different amount of time that we're going to go to, we're going to put a final time right here, okay, and that goes from 0 to final time now instead of 0 to 1. So what we're going to do now is go ahead and just take the inverse. Okay, the inverse of the M matrix, and that is going to be equal to n. Okay, so where n, I'm going to just rewrite this a little bit differently. I'm going to have Tn times n, and x1 dot, x2 dot, and x3 dot equals x1, x2, and x3 minus x naught for all of those. Okay, so we're going to have this, and the nice thing about this is if Tn goes to 0, if this time steps become very, very small, okay, if it approaches 0, then I just have equality constraints that basically just say, my x1 equals x naught, my x2 equals x naught, and my x3 equals x naught if Tn goes to 0. Whereas if you have it the other way, if you have it on the right-hand side, then as Tn goes to 0, there's a term that goes to infinity. So it doesn't work as well for these solvers that with very small time steps because you have very large, you have basically a very large term there that you got to try to solve. Okay, so we put it in this form, and then these N matrices have been derived for 2 up to 6 in the AP Monitor paper, but that you can go higher order as well. What I typically do though, if I need more accuracy, I don't have a higher order method. I just have more segments. So for example, let's say I had these 4 points, the one that we just derived, then I just put another one that attaches to it, okay, and I make these two equal, and I have 2 fourth order polynomials that approximate these different segments, and then as I need more time steps, I can just add more fourth order polynomials as I go out. Okay, so you can add also more time steps that are each approximated by a polynomial if you want to. Okay, so that's the derivation. Let's just do a quick example. Okay, so there's an example solution by orthogonal collocation. So if you come to this web address here, you'll see just a very an introductory problem right there, and then you have an exercise number 1 with the solution there and the source code. Okay, so you can look at the Python source code right there. You see your N matrices that are already typed in there for you, and so it sets it up. You got the different time points. One thing I forgot to mention is these are not evenly spaced time points, but those come from this Lobato quadrature that we're going to use to give us the optimal spacing, okay, between these time points. And so that's why it's called orthogonal. These orthogonal polynomials, this orthogonal collocation on finite elements. Okay, so that's the derivation. For a fourth order, I also showed you how to do it for a, basically a first order, and this one that is like the Euler's method, basically just a linear. Okay, the one that you're probably familiar with, but you can go with higher order methods as well. And basically, at the end of the day, what we're doing is we're taking something that looks like this. Okay, and if we had semi-explicit form, and we're translating that into another function that's just a function of algebraic variables. And the reason why we need to do that is because we need to solve this with nonlinear optimizers. So for example, minimize j of x, changing x values subject to differential. You can have a differential equation here. Or you could have, and what we're going to do is we're going to translate this into something that nonlinear optimizers can handle. Okay, so it cannot, nonlinear optimizers don't want to do with differential equations, so we're essentially discretizing them in order to get something that is an algebraic representation. Okay, so additional information on this, if you need more help on this, there are some references down below. Here's the one that's the AP Monitor paper. Okay, you can go with the Science Direct, or you can go with
Whoa. Oh, it sucks that I'm on incognito. Oops. Yeah. I don't know if that's a B or not. That's a super interesting looking B. It doesn't really look like a B. Damn. That's crazy. I didn't know that there was another way to do this. You can just directly solve. Bro, this guy got a forehead. Good for him, man. Brain. Oop. Wow, nobody uses this thing, but it's actually kind of badass. That's really fucking cool. In the worst case, there are simple higher index DAE systems with well-defined and stable solutions for which the backward Euler method and other multi-step method and RK methods are unstable or not even applicable. What is this, in Fortran? Nice. Yep. Bro, and they always do it as a single massive Fortran file. It's crazy. Yeah, the Fortran people are. Okay, well, I feel like I'm sort of gone down a rabbit hole of like other ways to solve DAEs, but the easiest and most simple way for me to conceptualize this is to just put it in a form that sundials can handle and then give it to sundials. Compile it and then give it to sundials. Get over. Alright, I did the motherfucking dishes. Did those dishes. Alright. Dude, what a lovely day. Just coding, bro. Just getting it in. Okay. Alright, so now what we want to do ice water. Delicious. Delicious. Oh, this is like such a good review. I don't really understand this thing of like why index 1 DAEs are fine. But whatever. For higher index systems, an index reduction is necessary to get a solution. This index reduction can be performed by giving appropriate options at NDSolve. NDSolve uses symbolic techniques to do index reduction. This means that if your DAE system is in the form of f of tx prime equal to 0, where NDSolve cannot see how the components of x interact and compute symbolic derivatives, the index reduction cannot be done. And for this reason, NDSolve does not do index reduction by default. Right, okay. Pendulum is the fucking classic example. I'm glad that I picked Pendulum. If I solve Pendulum, I'll be really happy. I'll go back out in a bit. Okay. Index reduction algorithms. NDSolve has two algorithms for doing index reduction, the Pantelides algorithm and structural matrix method. Both of these methods use the symbolic form of the equations to determine which equations to differentiate and then use symbolic differentiation to get the differentiated system. Both methods make use of the concept of structural incidence in the equations. In particular, if variable Vj appears in the equation EI, then Vj is termed incident in EI. The structural incidence matrix is the matrix with elements Mij equal to 1 if Vj is incident in EI and otherwise 0. A DAE system has structural index 1 if the structural incidence matrix can be reordered so that there are 1s along the diagonal. The existence of such a reordering means that there is a matching between equations and variables such that there is one equation for every variable. The Pantelides algorithm works with a graph based on the incidence that can be very efficient even for extremely large systems. Note that the structural index may be smaller than the actual index of the system. In the real system, terms that are structurally present may vanish along with some solutions, or the Jacobian matrix may be singular. The structural matrix method tries to take into account the possibility of singularities in the Jacobian and will do a better job of index reduction for some systems, but at the cost of greater computational expense. Okay. What is that awesome... So sick. If the structural incidence with respect to the derivative variables can be arranged to avoid zeros on the if the structural incidence with respect to the derivative variables can be arranged to avoid zeros in the diagonal, then the system is index 0. So for the case above, yeah, so I think that's fine. This is totally fine. Because with respect to the differential variables, there's no zeros on the diagonal. There's no way to... Okay. But... Okay. See, okay, yeah, I remember reading that, and I didn't understand why the tension is one of the highest order derivatives. That is still a question that doesn't really make sense to me. Get the structural incidence matrix for the constrained pendulum system with respect to the highest order derivatives that appear. Yeah, okay. The method proposed by Pantelides is a graph theoretical method that was originally proposed for finding consistent initialization of DAEs. It works with a bipartite graph of dependent variables and equations. And when the algorithm can find a traversal of the graph, then the system has been reduced to an index at most 1. A traversal in this sense effectively means an ordering of variables and equations so that the graph's incidence matrix has no zeros on the diagonal. When the bipartite graph does not have a complete traversal, the algorithm effectively augments the path by differentiating equations, introducing new variables, derivatives of previous variables, in the process. Unless the original system is structurally singular, the algorithm will terminate with a traversal. Generally, the algorithm does only the differentiations needed to get the traversal, but since it's a greedy algorithm, it is not always the minimal number. It is beyond the scope of this documentation to describe the algorithm in detail. The implementation built into the Wolfram language follows the algorithm pretty closely. It uses graph to efficiently implement the graph computations and symbolically differentiates the equation with D when differentiation is called for. When there is a traversal of the system, it is possible to find an ordering of the variables and equations such that the incidence matrix is in block lower triangular form. The BLT form is used in setting up the dummy derivative method for maintaining constraints and also in the state space time integration method. The description of the BLT ordering: bacon, lettuce, tomato, bro? That's crazy. That's crazy, bro. The BLT ordering, dude. Yo, I be ordering the BLT ordering all the time. The resulting system has index 1 since lambda still appears as an algebraic variable and does not contain a derivative in the differentiated system. Differentiating the system one more time will provide a differential system for lambda, therefore the index of the original system is indeed 3. As a first approach, the system with the twice differentiated equation can be solved directly. Zero differential order, I see. I think I called that index, differential index. Because when I print out I get 220. I don't know what this does. To model the original dynamics of the system with the new system, additional equations must be satisfied. However, including additional equations leads to more equations than unknowns. To address this issue, the method of dummy derivatives is used so that the index-reduced system becomes balanced. The Pantelides algorithm is efficient because it can use graph algorithms with well-controlled complexity for even very large problems. However, since it is solely based on incidence, there can be issues with systems that lead to Jacobians that are singular. The structural matrix method may be able to resolve such cases, but may have larger computational complexity for large systems. Okay. The structural matrix algorithm is an alternative to the Pantelides algorithm. The structural matrix method follows from the work of Unger and Chowdhury. The graph-based algorithms, such as the Pantelides algorithm, rely on traversals to perform index reduction. However, they don't account for the fact that sometimes there may be variable cancellations in a particular system. I think the thing is done. The structural matrix method follows from the work. This leads to the algorithm underestimating the index of the system. If a DA has not been correctly reduced to an index 0 or 1 system, then the numerical integration may fail or produce an incorrect result. Ooh. This implies that in order to get a system of ODEs, a second differentiation must be done for the second equation. The above system has non-singular Jacobian for the derivatives. The above system is now correctly index 0, and a system of ODEs can be formed from it. The actual system is index 2. So it seems like we actually have to implement the structural matrix method too. Okay. The matrix above contains a star as some of its entries. The star is used as a placeholder, indicating that the variables in that equation are present in the equation in a nonlinear fashion. Notice that for the second equation, the terms lambda and x appear as products. Therefore, the first and last are marked with a star. Oh, that's fucking cool, huh? Once the matrices are constructed, the objective is to try and convert the system of DAEs into a system of ODEs. In order to do that, the rank of the matrix JD must be full. To achieve this, the equations that need to be differentiated are first identified. In this case, it is the last equation. After differentiation, the structural matrices are... Okay. So... Oop. As usual, bro. Why is it always so good? I still don't know the answer. Like, if someone asked me, why can't you solve algebraic equations in a normal ODE solver? I don't really know what to say. Or even a DAE solver of higher index. Uses LawPack. Linear algebra is really beautiful, man. I mean, I wish I was better at linear algebra, but like, symmetric matrices have real eigenvalues. Kind of fucking cool, bro. Okay. Okay. Okay, well that's interesting to know about this other method. Ball. Stop ball. Stop ball. Stop ball. Okay, where were we? Wow. Trying so hard to get over you. Want to go back to place where we. Okay, so it does seem like there's a pretty decent. Okay. I think so. So then after that. I think it's drift, right? Trying so hard to get over you. Logarithm. The purpose of the dummy derivative method is to introduce algebraic variables so that the combined system of original equations and equations that have been differentiated for index reduction is not overdetermined. Consider the pendulum again. Is there a way to see which method is picked? Click to copy is so satisfying, dude. Note that for this example, the constraint method was included for emphasis and is not needed, since trying to use dummy derivatives is the default. Oh, here we go. Oh, wow. That makes sense. I mean, so you can solve for... Okay, so there's some method of probably finding all sets of dummy derivatives, and then you just look at those and see for what values the system incidence matrix becomes 0. Wow, this is a big ass problem. Okay, this is all starting to make a lot of sense. So, The alternative to using dummy derivatives is to reduce the index to 0. Okay. Okay, alright, so you take a DAE. I think there's a, isn't there that sweet picture? Yeah, okay, alright. That makes sense. Okay. But it does seem like you need a constraint method. So for DAEs, you need one, index reduction method, and two, constraint method. Then you can simulate. Okay. Oh, jeez. Dude, Wolfram is just the best system because it's symbolic first, bro. It's just clearly the right way to do things, man. Crazy to debug, but like, damn, is it beautiful. Just so many problems go away. Okay, well, let's go back and... Okay. All right, come on. It's time to get back to work. Do this fucking work, bro. So where are we at? We had just built A. And now we want to do step 3B, which is remove all vertices. Okay, so I'm going to clone B. Alright. Let's make sure that the they're not B, sorry, A. Well, yeah, so that's it, right? But is there something else we need to update? We need to update vnode. I love that tab complete, bruh. It's so good. It's so good. It makes coding so easy, dude. And so we need to do vnodes.remove k, right? Okay. But we also want to clone A. Wait, no, A doesn't get mutated, so we're fine. Like a G6, like a G6. No, what? What are you talking about? Oh. Oh yeah, this needs to be mutable. Wait. Oh wait, but if it mutates it, then I don't need to return anything. I think I could just return nothing. What did it say? Okay, so we're doing the right thing by not doing 2 owned. Oh yeah. Nice, so this one has none. I'm pretty sure that's right on. 4, 5, 6. Okay, so 3B seems to do what I need. All nodes. So that means we just clear it, right? Yeah, so if I have a mutable reference, how do I pass a shared reference to it? If foo has a mutable ref to var diff map and calls bar, which only needs a shared ref, what do? Alright, yeah, we can take it, give it a pointer. Trying so hard to get over you. Wait, but I don't want to give it the right to mutate. Oh, wait, hold on. If I did, like, let foo equal... Foo is, yeah, not immutable. Okay. That makes sense, buddy. That makes lots of sense, don't you know? Okay. Cannot mutate immutable G. What? Bro, what are you talking about? Alright, that's cool. Now, did I call it augment path? Does this modify the graph at all? No, I don't think this modifies the graph at all. So what we can do is we can just give it a pointer to G type. And I think that's fine. So we want to do that, right? Does augment path mutate any of its... No, because it doesn't change the graph, so if it doesn't change the graph, it doesn't change V nodes, E nodes, or G. So that's all good. Okay. If path found, break, else But do you break or do you return? No, I think you... Okay, so I'm not doing it because I'm scared that it's wrong. All right, so this ends up being pretty clean when you don't have to use maps, though. Okay, fine. Let me just do it. For every colored V node, so can I just do mute? For every color V node. Okay, so what does that mean? For every colored V node, you would take V nodes Is it a hash set? It's a hash set, right? I think I can do this, right? Oh, nice. Okay. For C V node, M plus equals 1. Create new so you need to add a new node. You need to add a new node, but what do you call it? Oh, that's so useful. Wait, but interestingly, whenever we modify the graph, like here, do we also need to modify num variables? I don't know about that. My guess is you definitely do. Wait, but it doesn't actually... No, this does remove nodes. Okay. Repeat until path found. So, no, I think breaking is correct. And then we set a... Oh, we do need to add G to add node. Oh, is that like super... Add node returns the node index. Okay, so that's That's actually all we gotta do. This bad boy right here. Okay, then for every colored E node, okay, so here we add a new equation, so num equations. What is the equation though? Oh, here I actually need to put in the... Is that right? I think I would. I'm not actually certain if that's true. please just do it? This equation should have But which one? But which one? Well, I don't actually understand why you need to add new variable nodes. At this point, for every colored V node. Why? Okay. What is this? Okay. Yeah, I don't know what the hell that part means. Create edges from E node N to all V nodes J V nodes J and AJ such that edge LJ exists. What the hell is L, bro? I feel like I had this yesterday. So all this is saying is that, what is J, bro? Or what is L? Oh my god, dude. Bro, I'm literally so dumb. L is the new E node. Right, okay. Such that from the new E node, Okay. I'm starting to get this. So okay, so what this is telling me is that for all of the colored E nodes represent equations that need to be differentiated. So you increment the number of equations, you create a new equation node, then you create edges from this new node to all. So in the set of I don't really get this. Like, isn't all V nodes I'm guessing what he's trying to say is that I think he means that if you have like the x squared plus y squared minus l squared expression, you differentiate it so you get 2x dot x plus 2y dot y. Oh wait, I think we want to do. Oh, I get it. Bro, I get it. Okay. Yeah, so it's saying if it's saying if yeah, it isn't clear what the condition is. I think this is what this is saying. This part is Susi. That should be in the order in which it was appended. So J should be the second one. Is that a thing? What is it called? Private, bruh. What? What is the point? Literally, what is the point? What methods are there on this thing? Edge reference. I don't really understand why they always do this. This is so crazy. Oh wait, hold on. It's the same type, dude. What? This edges type is like bogus, dude. Wait. No, but those aren't pub, dude. Oh, I guess I could collect it, right? Is that what I'm supposed to do? .iter.collect. No, why, bro? Oh, it only implemented into iter, I guess. Oh, wait. Oh gosh, that's so stinky, bruh. Can I get neighbors? Is it gonna be the same story though? That's the question. No, it implements iterator, so I should be able to do dot iter. Oh, what? Okay, that's fine with me. So these are all of, so that means that for n in I guess that is the assert. Deref. Deref. What? Oh. Do, 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 do. Alright, I mean, I think we did it. So now we have the nodes. We have we have all the J's. So these are the J's. so what we want to do is g.addEdge. Bruh, get me out of this thing. Create edges from enode n. Num equations is going to be e nodes.len v nodes.len. It's going to be mute g3. Var diff map is just a, right? Interesting. This is an augment path. Frick. Oh yeah, hold on. But you can't give it as you can't. Give it a 0. Oh, there's just so many things that could be wrong. Okay, so the question here is, are we guaranteed that a sign Oh, you just can't. Yeah. Okay. Yeah. That's cool. All right. Maybe I'm giving up for right now. I might come back on, but like, God. The problem is I just don't really understand the algorithm. Where does print J happen? So I think it did find the 4 good ones, and they were the 4 later ones, but then we panic when we actually get to the... Okay.